Question 3. The graph shows how the gravitational potential varies with distance in the region above the surface of the Earth. R is the radius of the Earth, which is 6,400 kilometers. So just our usual thing. Just being careful about units. At the surface of the Earth, the gravitational potential is minus 62.5 megajoules per kilogram. So minus 62.5 times 10 to the 6 joules per kilogram. Use the graph to find A, the gravitational potential at a distance 2r from the center of the Earth. Okay, we're going to draw quite a lot of lines on here, so we'll try to use a different color each time and maybe a fairly thin pen so that we keep as much of the information as possible. So at 2r, we're going to come down and across. Obviously, one note judging interception of lines isn't great, but we're only going to say we know this to the nearest whole square anyway. So this is at 32, I'm going to say. So write our answer in a slightly thicker pen. So minus 32 megajoules per kilogram, or minus 32 times 10 to the 6 joules per kilogram. B, the increase in potential energy. So it's important to note we've got this word energy in here. Use a different color. Of a 1,200 kilogram satellite when it's raised from the surface of the Earth into a circular orbit of radius 3r. So coming back to my graph, I need to take another pair of readings at 3r. So because in the question it says use the graph, we should be putting markings on the graph each time. This is a fairly standard thing in, well, physics questions, A-level and GCSE. That looks to be about halfway across, so I think it would be reasonable at this point to say that that's at 21. So using our graph, we can say that the value of the potential at 3r is minus 21 megajoules per kilogram. So to work out the energy, we're going to take the mass and multiply it by the potential difference. So in this case, the mass is 1,200, and then we multiply that by the final minus the initial. It's always our way. So we're lifting up. So the final is minus 21. Remembering this is times 10 to the 6 minus the initial, which it tells us up here, 62.5. 62.5 times 10 to the 6. So we can work out the value of this is, again, two significant figures. So 5.0 times 10 to the 10 joules. Find the gradient of the graph at the surface, at the height r above the surface, and the height 2r above the surface. So we're going to try and take readings for 3 different gradients on our graph. Again, we'll try to use a different color each time. So let's do the first one in this green. The first one's the hardest because we have to draw a tangent at the point where the line stops. So we're trying to draw something that's about right. It's hard to do, but that's our first gradient that we've got there. So as always with these, we try to draw a big triangle. We'll try to use relatively easy values. Let's go for that point there. That looks like a good one. So on the green triangle, we've got it starting at minus 10 and going down to minus 80. So we're going to do, in green we're working, aren't we? So the gradient, so I'm going to call it, let's call it M. So the change in Y is of from top to bottom, so it's going to have a positive gradient, I can see already, so I won't worry too much about signs. We've got a difference of 70 times 10 to the 6 on the y-axis, and on the x-axis that's looking across this way. This is at a point of 1.7 r. I'm going to write that there so I don't forget, and this one is about halfway between those two marks, so there, so about 0.75 r. So the difference between the two is 0.95 times r, r being the radius of the Earth, so 6.4 times 10 to the 6. So we need to calculate that. So that gives us 11.5. Now, because we've taken this a gradient, I think it's reasonable to round it to two significant figures. So we're going to put 12. We should put a unit on this thing, of course, so we have to think again about the unit. So we've got megajoules per kilogram in this one and meters on this one. So we might be tempted to put megajoules per kilogram. No, not megajoules, of course. We took that M into account, didn't we? Per meter. But when we see the joule and the per meter together, we might think about the work done formula and say that actually a better unit here would be newtons per kilogram. Okay, then we're going to do part 2 at a height r above the surface. So we'll go for another new color. Let's go with this orange. Thin line, 2r is here. Use our ruler. Use our ruler. Get this lined up as best we can. So there, looks fairly good. Straight line. Again, we want to pick some points off. So this looks like a good point. Let's say it crosses right at that axis there. And I'm going to come down to this point here. Obviously, on your own, you might choose different points. So putting some values on so I don't forget them. This is at a distance of 4r. This one is at a distance of 0.8 r. So the change in the x-axis is 3.2 r. Let's put that in now. M is something over 3.2 times 6.4 times 10 to the 6. And on the top, we want the change in y. So it goes from 0 to 50. Again, we won't worry too much about the signs because we can see the gradient is positive 50 times 10 to the 6. Of course, to make our calculation easier, I should do that, shouldn't I? That would save me lots of time calculating. So 50 divided by 3.2 times 6.4 gives me 2.44. So I'm just going to write down 2.4. And again, that should be in newtons per kilogram. Sorry, I'm not in the habit of writing the units correctly for A level. And then at a height 2r above the surface. So one more of these at 3r. So we need one more new color of pen. There we are, that looks good. What have we got left to use? Let's use this light blue color. Draw a tangent on at this point. Again, we need to mark two values on. I didn't keep it going down to that line. That was silly. Let's see if I can just extend it slightly. Not the best at that point, is it? Hey, let's go with it. Draw my triangle on. I'm going to share that orange line that I've already used. No, let's go up to this next one, actually. There we are. Doesn't need to be straight. Let's just draw that in by hand. So this is at a distance of 4.5 r. This end is at 0.4 r. So we've got a change in x of 4.1 times the radius of Earth. And the change in the y-axis is the height of this thing. So it's at minus 40 there. And we're at an awkward point there, aren't we? I think I'm going to say that's halfway between the two. I think it's closer to halfway than the top, but that's debatable. So that's 9. So 40 minus 9 is 31. 31 times 10 to the 6. And then again, let's do that to make our life easier. So we've got 31 divided by 4.1 times 6.4, which is 1.2 newtons per kilogram. And then D says suggest a relationship between the gravitational potential and the gravitational field strength. So with our results, we can just about see this. The first one perhaps will have put us off slightly, but if we say CI is approximately equal to 9.8 newtons per kilogram, CII is approximately equal to 9.8 newtons per kilogram over 4, and part 3 was approximately equal to 9.8 newtons per kilogram over 9, then hopefully we can see that the gradient of the gravitational potential graph, so that would be dV by delta R, is equal to, we might be tempted to put the gravitational field strength here, except we know that this graph has a positive value and the gravitational field strength is always negative. So this graph is suggesting to us, hopefully, that the gravitational potential is equal to minus the gravitational field strength.